In this video, I'm going to show you how to simulate a Mecademic Meca500 6-axis robot. After watching this video, you should become more familiar with setting up the physics, joints, and motors for an industrial robot, and be able to create basic robot programs inside ProtoTwin. I'll start by importing the CAD for the Meca500 robot into the main application. If you would like to follow along, you can find a link to the CAD in the video description, or the document for the CAD model on Onshape. If the import is successful, you should see a visual representation of the model in the viewport. We can now begin to add components to the various parts and links of the robot. I'll start off by control right-clicking. Then I'll select the Link 1 entity from the hierarchy. I'll now add a physics component to this entity. I'll also set the collider type to none, since we're not interested in modeling collisions or measuring the torque. I'll now add a joint, set the constraint type to revolute, then configure the axis and anchor properties by selecting appropriate features from the mesh. These properties define the plane and point about which the link is allowed to rotate. You can click the Add button next to the motor property to quickly create a motor component that is bound to the joint. I'll change the target speed of the motor controller to 180 degrees per second, and the target acceleration and deceleration to 360 degrees per second squared. I'll control right-click again, then select Link 2 from the hierarchy. Just as before, I'll add a physics component and set the collider to none. I'll now add a joint, set the constraint type to revolute, then configure the axis and anchor properties by selecting appropriate features from the mesh. Now we need to connect these two links together. We can accomplish this by setting the base property of the second link to the first link. This will constrain the second link so that it is only permitted to rotate relative to the first link. I'll now add a motor again and configure the target speed to 180 and the target acceleration and deceleration to 360. The process for the remaining links is the same. I'll first control right-click and select Link 3. Next, I'll add a physics component with the collider set to none. I'll now add a joint, set the constraint type to revolute, then configure the axis and anchor properties by selecting appropriate features from the mesh. I'll set the base property of Link 3 to Link 2, which ensures the links are connected. Finally, I'll add a motor and configure the target speed, acceleration, and deceleration to the same values as before. Alright, I'll control right-click again and select Link 4. I'll then add a physics component with the collider set to none. I'll now add a joint, set the constraint type to revolute, then configure the axis and anchor properties by selecting appropriate features from the mesh. I'll set the base property of Link 4 to Link 3 to connect the links. I'll add a motor component and configure the target speed to 180 and the target acceleration and deceleration to 360. I'll now repeat this process for the remaining two links. I would just like to note briefly that the Meca500 robot uses different values for the angular speed and acceleration of each joint. Moreover, the real robot includes joint limits, which we did not configure here for simplicity. If you would like to model the joint limits with the true motion parameters, you can find a link to the technical specification for this robot in the video description. To apply joint limits in ProtoTwin, you need to enable the checkbox and then enter an angle next to the limits property for the joint. It's not a strict requirement to apply joint limits for this model, since all the moves used here are valid moves. However, it is still worth applying them in other robot models you make, since the robot controller component in ProtoTwin will automatically detect any moves that violate the joint limits, and will output an error whenever the robot is unable to solve the target. When you've finished adding the joints and motors, it's important to run the simulation to test if the robot is behaving correctly. If you watch closely, you'll notice that the last two links are shaking slightly. This instability can be caused by a number of reasons. Always make sure to reset the simulation before making persistent changes to your model. The first reason is that the relative mass of all the links is the same, even though link 6 weighs significantly less than the other links. So I'll change the mass of link 6 to 0.1 kilograms. I'll also select link 5 and change the mass of link 5 to 0.5 kilograms, which should help improve stability. The second reason is that the solver settings may need increasing. So I'll open the model settings, then in the physics tab, double the number of iterations performed by the solver. If you run the simulation again, you should notice the robot no longer shakes. Since this robot is only 9 by 9 by 33 centimeters, you may also need to reduce the time step when gripping small parts. though for just simulating the motions, this is not required. I'll now select the entity for the robot, then add the robot controller component to this entity. We first need to configure the TCP, which is the tool center point for the robot. For the TCP, I'd like to use the center of the sphere on this pin entity here, so I'll first select the pin, and then add the robot TCP component. This component will allow us to precisely position and orient the TCP. I'll first select the position as the center of the sphere. Then for the rotation, I'll apply a 90-degree rotation about the local x-axis. I can select the robot entity again and then configure the TCP property as the pin entity. We're now ready to create the robot program. You should notice 4 yellow spheres depicting the teach points for the robot. The robot controller component will solve the frame of the TCP to the frame of a target teach point entity. I'll first add an instruction to the main program and set the type of the instruction to joint move. I'll then select the target as the first teach point, TP1. You should now see a visual representation of the frame of the TCP and TP1. As I mentioned before, the robot controller will move the motors so that the TCP frame corresponds to the frame of the first teach point. I'll reset the simulation again and add the remaining instructions. For the next instruction, I'll add a linear move and set the target entity to TP2. This will instruct the robot controller to move the TCP along a line from its current pose to the target pose defined by TP2. I'll add another linear move instruction again, but this time the robot controller will move the TCP of the robot back up to TP1. Now that the TCP is back at TP1, I'll add a joint move instruction, which will move the TCP of the robot to TP3 on the right side. I'll now add a linear move instruction again, which will instruct the robot controller to move the TCP along a line down to TP4. Finally, I'll add a linear move to move the TCP of the robot back to TP3. With the instructions now complete, we can run the simulation again to test the program. You should see the current instruction being executed by the robot controller component highlighted in green. The highlighted instruction tells you the current move that is being performed. Let's say we want to modify some of the target frames. I'll now select the entity for TP3 and change the orientation to 45 degrees about the y-axis. I'll do the same thing for TP4 too while I'm at it. The gizmo will show you the new target frame. If we run the simulation again, you should now see the updated motion for the robot given that we modified the orientation of the TP3 and TP4 entities. You can hover over an instruction in the list to inspect the frame of the target entity for that instruction, as well as the frame of the TCP as the instruction is being executed. I'll reset the simulation again and double right-click to focus the camera on this entity. Suppose we want to create a new teach point. Well, I can select the entity in the Explorer pane to the left, and then right-click and copy the entity. I can then paste this entity as a child of the main entity. I'll now rename the entity to TP5. I'll update the orientation to rotate about the z-axis by 45 degrees. I'll now copy TP5 and paste it as a child under the main entity. I'll rename this new entity to TP6 and update the orientation of this entity to an angle of -45 degrees about the z-axis. I'll select the robot entity again and add some more instructions to the main program. I'll first add a linear move instruction to TP5. Then I'll move this instruction up in the list so that it comes after the linear move to TP4. I'll then add another linear move instruction, but this time select TP6 as the target. Once again, I'll move this instruction so that it comes after the move to TP5. Finally, I'll add a linear move, but this time moving the robot TCP back to TP4. This instruction will come before the movement back to TP3. So it will move the TCP to TP4, then to TP5, then to TP6, then back to TP4 again, and back again to TP3 at the very end. If we run the simulation again, you should see the motion of the robot update according to the new teach points we created. Notice how, in the movements at the end, the TCP of the robot is not changing position, but it's only the orientation of the TCP that is being updated. This is because we decided to use linear movements instead of joint movements, so the position remains constant and the orientation undergoes linear interpolation. I hope this video gave you a better idea on how to model a 6-axis robot and control the robot to perform a bunch of movements inside ProtoTwin. Thanks for watching.